Hi everyone. Okay, in today's video, I'm going to show you how to solve for these questions, which is to find the electric flux density and also the electric field by using the Gauss law. Okay, so let's go through the questions together. So let's row L. Okay, so this is the line charge density. So the line charge density is 2 nanocoulombs, okay, for both the R equals to 1 centimeter and R equals to 3 centimeter in the figure. So you can see this figure is a coaxial line, so you have inner conductors. Okay, so this is your inner conductor and it has the radius of 1 cm. Okay, 1 cm. So if you convert it to meter, it is 0.01, and it has outer radius of 3 cm, which is equals to 0.03 meters. Okay, so their line charge densities are 2 nano, means that this one itself has 2 nanocoulombs per meter, and this one also has 2 nanocoulombs per meters. Okay, so you can imagine, so okay, positive charges, okay, they are on the line, okay, on the surface of the line, okay, because there has line charge density, okay, line charge density, yeah. Okay, so in the regions in between 1 cm and 3 cm, which is the blue color regions, okay, this is the regions, it is filled with free space. Okay, free space. Okay, what does it mean when we say that the medium is free space? It means that the epsilon is equal to epsilon naught. So you have to find the electric flux density and also the electric field, okay, in between 1 cm to 3 cm and greater than 3 centimeter. Okay, so this is our task. All right, so to solve for this one, we have to apply the Gauss law, right? Gauss law. So in order to apply the Gauss law, the first step is we have to construct our Gaussian surface. Okay, Gaussian surface. I hope you still remember what is the criteria and conditions for a Gaussian surface. Okay, if you forget, you can actually refer back to your notes. Okay, right over here. Okay, you can flip back to your notes and go to the sections, okay, of the Gauss law. All right, Gauss law. Right. Okay, so this is the criteria for the Gaussian surface. So the Gaussian surface must be a closed surface, okay, and this surface is chosen so that the electric flux density is normal or tangential to the surface. Okay, when it is normal, it will be values, okay, maximum flux passing through the surface. But if it is tangential, okay, the dot product between the electric flux density and also the Gaussian surface will be equals to 0. So the shape of the Gaussian surface will resemble, okay, the shape of the charge distributions. For example, if it is point charge, okay, the shape of your Gaussian surface will be spherical. Okay, if your charge distributions, okay, is a line charge, for example, line charge distributions, so you will build your Gaussian surface to be in the shape of cylinder. Okay, so these depend on the shape, okay, the dimensions of the charge distributions. Okay, so we must make sure that there is symmetry exhibited by the charge distribution. So this is the criteria for the Gaussian surface. Right. So now let us look at this case. We have to find the electric field at the region that is in between 0.01, I convert it into meter, and also R, okay, and 0.03, okay, 0.03. Okay, so if you view this coaxial transmission line from top, okay, you view it from top, okay, so this is your inner conductor, and this is your outer conductor, right? So you are required to find the electric flux density and also the electric flux density and also the electric field in between 1 cm and 3 cm, okay, which is these regions. Okay, so the first step is we construct the Gaussian surface, right? So this is our Gaussian surface, right? Gaussian surface, okay. So I construct my Gaussian surface, and after I construct my Gaussian surface, I have to apply, okay, I have to apply the Gauss law. Okay, so what the Gauss law say? So Gauss law says that the total flux that is coming out from the Gaussian surface is equals to the charge enclosed by the Gaussian surface, right? So this is the Gauss law. Okay, so we need to identify the flux that is coming out, okay, from the Gaussian surface. Okay, so we know, okay, for the inner radius, okay, it has rho L, positive rho L. Okay, so the flux that passing through, okay, your Gaussian surface will be in the R directions. Okay, will be in the R directions. Okay, so since the shape of the coaxial transmission line is cylinder, okay, so in this case, we apply the cylindrical coordinate systems to represent the directions of our D as well as our E. Okay, so this is the direction of the flux. Okay, so we will put double integral. So the directions of our flux is the R directions. So since we are picking cylindrical coordinate systems, so the ds, we have to refer the ds for cylindrical coordinate system, and we have to use the surface, okay, that is facing the R direction, which means that I have to pick R, d phi, and dz. Okay, and in the R directions. Okay, so this is the directions of the Gaussian surface facing. Okay, on the other hand, okay, the charge that is enclosed by the Gaussian surface. Okay, look at our drawing here. Okay, this is our drawing, right? Our drawing. Okay, so you can see that your Gaussian surface only cover the inner conductor, right? The inner conductor. Okay, and the inner conductor has been given a line charge density rho L. So if you want to find the Q, we have to perform integrate rho L dl. Okay, so we have to specify what is the length. Okay, how long is the inner conductor? Okay, so by referring to the image or figure, okay, the length of the inner conductor is 0 to h. Okay, so we write this down. And next, on the left hand side, we are going to determine the range for the phi. Okay, phi is the angle. Okay, angle for if you look at this figure, okay, the angle of the rotations of this Gaussian surface. Okay, so it is a complete circle, so the radius will be from 0 to 2 pi. Okay, and the z represent the length of your coaxial line. Okay, right? Okay, so it will be from 0 to h. Okay, 0 to h. Okay, so we simplify by performing the dot product. Okay, dot product in the same directions will give us 1. Okay, so if you're not sure about this dot product or cross product, what is the value, right? You can always refer to the formula sheet. Okay, so the formula sheet that is given, okay, in the exam, you can refer it. Okay, right, so we have simplified the dot product of unit vectors. So now we are going to do the integrations. Okay, so for this, we are going to get dr, right? And we are going to get 2 pi, and we are going to have a h here. And on the right hand side, okay, we are going to get rho L and h. Right, so rho L, the value has been given by the questions, right? It is 2 nano. Okay, so we can write down 2 nano here. Okay, 2 nano. Right, so the h, you can cancel out. So the electric flux density will be equals to 2 nano, okay, divide with 2 pi r. Okay, 2 pi r. So you can simplify by cancelling the r. So it is 1 nano over pi r. Okay, if you want to specify the directions, you can put the directions, okay, which is r directions. Right. Okay, so for the electric field, okay, you can use the relationship, okay, which is D equals to epsilon naught E. Okay, so this is the relationship, okay, of the electric flux density and also the electric field. So as a result, you will have 1 nano over pi epsilon naught r and r. Okay, so we use epsilon naught because it is free space. Okay, so that's why we use this. So this is the electric field in the region between 1 cm to 3 cm. Okay, region between 1 cm and 3 cm. Okay, next we move on to the next region, which is r greater than 3 cm. Okay, r greater than 3 cm. Okay, so for the second case, okay, second questions, we are required to find the electric field and also the electric flux density when the r is greater than 3 cm. So let me draw again, okay, my line, my coaxial line. Okay, so I have inner and outer. So 3 cm, greater than 3 cm actually refer to these regions. So I construct my Gaussian surface covering, okay, my coaxial line. Okay, covering my coaxial line. So for the outer conductor, it has the line charge density, rho L, okay, positive. And for the inner conductor as well is positive, and both of them, they are positive charge, right? So the electric flux or electric field, okay, they will be going out in this way, right? Going out in this way. Okay, so again, it is in the r directions. So after you sketch the Gaussian surface, after you identify the directions of the D and also the direction of the E electric field, we write down, okay, our Gauss law. Okay, so for the left hand side, it is exactly the same like the first part. Okay, so you will integrate from 0 to h, okay, 0 to 2 pi. So you have d, r directions, and you have r, d phi, dz, okay, and in the r directions. So r, so over here is the Q, okay, total charge, okay, that is enclosed by the Gaussian surface. Okay, so we can look at this drawing again, okay. So you can see your Gaussian surface is enclosing two charged objects, right? So the first one is the outer conductor, right? The first one. And the second one is the inner conductor. So the Gaussian surface enclosed two charged particles, okay, that is the inner, okay, and also the outer. Okay, so we have to look for the Q from the inner and also outer. Okay, so what we should do here is, okay, let me simplify the left hand side. So the left hand side, okay, this is dot product, so I can simplify it to be dr, okay, and 2 pi and h, right? And for the right hand side, we will integrate from 0 to h. Okay, so the rho L is 2 nano, okay, for the inner. So the dl, I write down here. And for the Q outer, okay, so it is also represented by these 2 nano of line charge distributions. So over here we have 2 nano h, right? Okay, plus 2 nano h. Okay, so we have 4 nano h, right? 4 nano h. Okay, so let me write down this. So you have 2 pi, you have h. So the h you can cancel, right? So the d will be equals to 4 pi, it's only 4 nano, divide with 2 pi r. So you can simplify it to make it to be 2 nano, right? 2 nano, so it will be 2 nano pi r. Okay, so this is the electric flux density in the r directions. And for the electric field, it will be equals to 2 nano over, okay, epsilon naught pi r in the r directions. Okay, so this is the electric field and also the electric flux density at the positions the r greater than 3 centimeter. Right.